the steam will be used to generate a steam turbine generators. So those are the techniques available, but you need to expect more and more inverters are going to be there in the system. When inverters are there, there is power electronics devices there which can create harmonics into the system. So that's a problem with the power quality. Okay, so that we'll discuss about that in detail. So we talked about the smart grid. What are the components involved in the smart grid? And these are the functions of smart grid. I mean, in general, smart grid can be considered as a bidirectional flow of power and data. When you talk about the data, all the data is available at a central location when it comes to smart grid. Then you can develop different systems to operate the grid in a much better way, in a much economical way or much efficient way, with utilizing the technologies available, or maybe the software technologies available. You can utilize the system in a much better fashion, like maybe SCADA, EMS. Maybe EMS refers to transmission system, or transmission or generation system, energy management systems in transmission and generation. DMS is again the energy management system in distribution system. There are different parts, substation automation, and mainly in the distribution. Wide area monitoring system, which is basically with PMU arrangement, monitoring the entire system, healthiness of the system, etc. will be monitored, and suitable action will be taken in order to make the system stable even before some adverse event happens. So that is the importance of the wide area monitoring system. AMI, the smart metering, cybersecurity is very important when it comes to handling of the data, and we are putting all the data related to the grid into a communication network. Cybersecurity is going to be a major concern. Energy storage, we talked about it. What is the requirement of energy storage, and what are the concern brings? Like when we talk about the energy storage, again the inverters are going to be there. So it is going to be, creating power quality issues. Uh, Electric vehicles, again, we talked about a charging station, creates power quality issues. Renewable energy integration, definitely it is going to be mostly with the solar or even the wind, going to have inverters, power electronics devices. It's going to create power quality issues. So power quality management is one of the important function of smart grid. You need to manage the power quality, or maintain the power quality. For that, you need to have metering system or monitoring system for power quality. And wherever the power quality is lesser, you need to strengthen the system to make the power quality better at that area. Okay, outage management system, distribution transformer monitoring system, control room, common control room, enterprise IT systems, analytics, which includes artificial intelligence based systems, GIS mapping, which is for the mainly for the asset management, then customer engagement, social media. All these things will be taken from the, it's going to be part of the smart grid. Mobile crew and engagement management system, mainly for the maintenance part, like how to mobile the technicians or the engineers to repair some part of the system if there is an issue. So it is also going to be part of smart grid. Smart lights, smart street light, etc. We have seen some part of smart grid is creating power quality issues. Energy storage, electric vehicles, renewable energy, power quality management is required in order to manage that power quality. Okay. So this part we already talked about it. What are the features of smart grid? I'm not going to that detail. So let's discuss about the power quality. Okay, let's try to understand what we mean by power quality, right? Uh, Maybe a general lookout, maybe for a normal consumer will be like, when he say that power, I get a good quality of power. He means that the power interruptions are lesser, probably it's very less, or maybe the voltage variation, which can be seen, which can be seen maybe from the I mean, lights itself, that you can sense that. I mean, one can sense that the voltage variation is there, fluctuation is there, or maybe is there an issue with some equipment what is using in home. So the voltage variations or interruptions are the major criteria that one will be one will be assessing the power quality. I mean, that's the general lookout of it. But definitely the power quality is decided by the overall grid performance. So when the electrical engineers talks about the power quality, he doesn't just think about the voltage variations or interruptions, right? It has a lot of other features, I mean other factors also, which is frequency variations, one of the important factor. Voltage, because frequency variation can create some issues, especially in the rotating loads or even power electronic device, because they takes probably the zero crossing, or maybe like in the control they will take that part. So maybe the frequency variation might create an issue the power electronics devices also. Voltage dip, voltage swells, increase in voltage or dip in voltage. Voltage dip can be because of the motor starting or some major load, energizing some of the major loads could be the issue. Could create an issue in with respect to the voltage dip. Voltage swells is something like the increase in voltage during some time when you disconnect some major part of the load from the system. Probably it can create an increase in voltage. So short time and long time interruption, that is straightforward. Short time, generally we talk about the interruption less than 2 seconds. Maybe long time it's more than 2 seconds. Short time probably like there is a fault, maybe the protection system operates and clears the fault and takes maybe 2 seconds to clear the fault. So during that time there will be interruption, or maybe voltage will not be available to the consumer. So that can be considered as short interruption. Long interruption is something maybe could be some scheduled interruption could be there, or maybe unscheduled tripping of a feeder because of some fault on the feeder. Harmonic distortion, this is the main thing which we are going to discuss today, because that is more related to the smart grid integration. Other part is related to the primary system itself, but harmonic distortion is it can be created because of the components in the smart grid integration itself. Voltage fluctuation, you can see the voltage is fluctuating, like it goes higher, maybe it gets reduced, and again next cycle, after a few cycles it goes higher again, it goes like that. So that's a fluctuation again as a power quality issue. Noise, I mean, there is a noise, high frequency noise signal is superimposed with a sinusoidal fundamental frequency signal. It creates the, I mean, it modifies the overall shape of the waveform here. And voltage unbalance, we know that we are using three-phase system. So it is expected to be having the same magnitude of voltage in all the phases, and the phase angle is shifted by 120 degree apart for each phases. So that is what is called a balanced system. But when the voltage is going to be unbalanced, then the magnitude also can be different phases. So that can create issue mostly in the rotating machines. Rotating machines, motors can be overheated because of unbalance. It cannot handle unbalance. Maybe the maximum unbalance percentage that it can handle is maybe 8% or 10%. But if it more than that is going to create a overheating the motors, the motor can be burned because of unbalance. So let's try to understand how the world is looking at power quality. Okay, just to give a hint of how benchmarking is done, or how the reputed utilities are competing with their counterpart from other countries. Probably this is good to know some of the indexes. Like one index is SEIDI, another one is SEIFI. These are two indexes. One is System Average Interruption Duration Index. Per year, how many minutes of interruption is expected in the system for a consumer, for a particular consumer? Particular in the sense, in average, for a consumer, how much hours of interruption is expected or happened in the system, right? That is what it is. And safe is nothing but the frequency, how many number of times it happened. So, I mean, I was working with the Dubai State, I mean, Dubai Electricity and Water Authority earlier. So, this is the data from their website basically. This is their claim. Like you can see, like Saidi, I mean, what they say that as per their statistics, uh, in the year 2020, the number of minutes the consumer uh, didn't have the supply for any year is only 7.61 minutes. Okay, which is, I mean, they was considered to be one of the reputed utility with respect to this, I mean, indexes. And you can see that on this is what is expected in Diva. I mean, what happened in Diva in 2020, on an average, a consumer lost 7.61 minutes of power in 1 year. So we can try to understand like where they stand and where we stand. I mean, why I'm saying is that we have lot of scope for improvement in India. That's what I'm trying to say. Like you need to come up with. There are a lot of scope for research also to make or to compete with this level. I mean, what world is at now. I mean, when you talk about some European countries, they are at maybe 15, 20 minutes, or maybe within 100 minutes. Probably most of the European countries that's a number of minutes. I mean, that many minutes interruption is expected in their system for a consumer. I mean, the other one is that the frequency index. I mean, number of times the power is lost. Okay, you need to understand one thing. It is based on some IEEE standard. These indexes are based on some IEEE standard. So momentary interruption less than 5 minutes are excluded while creating this. So you need to understand that momentary interruption less than 5 minutes are excluded in that. So it says that number of interruptions is, I mean, less than one, which means that maybe if you take 10 consumer probably, or maybe 8 consumer, probably only one consumer is experiencing interruption in a year. That's the status of Diva. uh, and there are some, I mean, reports also. I mean, World Economic Forum reports are also. I'm not going into the detail of it. I mean, most of the European countries are topping the list there. I mean, some of the Middle East countries are also topping the list there. And our I mean, Indian position is not even within 50. So which gives you an understanding like where we are in terms of power quality, and what all research opportunities are there in the power quality related parts. So you can think about that, and you can try to benchmark it with other utilities to come up with some research papers, like what to be done to maintain and to compete with other utilities. So just to give I mean, information on that, I have put this slide. Okay, so let us try to understand what is the Indian grid requirement, right? I mean, okay, this is just to give a hint of like what was the quality. I mean, frequency variation. It happened on 13th November 2021. I have taken it from POSOCO website. You can see that from this website, POSOCO website. Like every day the frequency variations will be declared, I mean, given like this. So you can see like it's like frequency is stable in India. You can see like frequencies varying from about 49.7 to almost like 50.12, which was not the case few years back. Maybe if you take the case, maybe 20 years down the line, maybe the variation was much higher. Maybe you can expect a variation from 49 to maybe 51, something like that. So nowadays it's very much improved. It's very clearly visible here. uh, you can see the voltage dip. I mean, when we talk about the voltage dip, you can understand like it's a distribution system. When I try to start a motor, when you try to start a motor, this is how it is. The dip can go up to maybe 15%. Right now it shows only 5 to 8%, but it can go up to 15%. If you energize the largest motor, you can expect about that. But maybe for the point of interconnection, probably that is limiting up to 5%. That is what it's showing here. So 5% dip you can expect at the point of connection, probably when one of the largest motor starts. It is stepping down. I mean, it is reducing from or dipping from 228 volt, or maybe 230 volt, maybe around 230 volt to 218 volt. And but this is okay probably if it happens only once in a day or something like that. But if there is I mean industry which based on the process requirement, this motor need to be started in every hour or something like that, what is going to be the issue? You can see here, this is the waveform of the repeated motor starting. That's a dip every 1 hour or maybe every half an hour or something like that. We cannot consider it as a, I mean, good quality or good quality system. So these are the issues. And when you talk about the fault, definitely when the fault happens, the voltage collapses locally, probably at the location of the fault. Maybe if it is a three-phase fault, the voltage will go to zero. But if it is slightly away from the fault, probably you have some voltage, maybe slightly more, but I mean, slightly more than zero, but you need to consider it as like there's no voltage during that time. But when the protection system operates and isolate the faulty part of the system, the voltage will be improved close to the rated voltage again. So you can have an interruption like this, depending on the speed of protection system. I mean, you can experience. I mean, the consumer can experience a dip in voltage. Here in this case, the I mean, protection system is faster. Probably it is operating within 100 to 120 millisecond, less than a second. I mean, probably it happens when there is a unit protection, I mean, differential protection or something like that. You can, I mean, distance or other type of unit protection, then you can expect the voltage improves or maybe the fault clears within 100, 150 millisecond. But when it comes to distribution system, generally distribution system relies on the overcurrent protection. So you need to expect interruption time of almost like 1 second. So probably that interruption time is increases to 1 second in the case of distribution system. So these are the grid code requirement with respect to the power quality. The frequency is I mean, the limit with respect to the Central Electricity Authority regulations available in CEA website. It gives like frequency limit is 49.2 to 50.3, and the voltage limit is mostly plus or minus 5% variation up to 400 kV. But when it comes to 220 kV and down, it is plus or minus 10% variation is allowable as per the grid standard or grid code. As per the grid code, it is allowable. When it comes to the unbalanced limits, probably you can see here in the extra high voltage system, the allowable unbalance should be limited to 1.5%. When it comes to 220 kV, 2%. When it comes to 33 kV to 132 kV, it is 3%. When it comes to the distribution voltage level, generally I mean, it is allowed up to 5%. The temporary voltage limits because of some load rejection or something, or maybe some single phase fault, and then other healthy phases can experience a higher voltage. So this is the limit of temporary over voltage. You can see like 132 kV system, temporary voltage is allowed up to 170 kV. And when it comes to 765, 914 kV is allowed. This is the RMS, I mean 50 hertz voltage we are talking about, power frequency voltage which we are talking about. Again, for the voltage fluctuation limits, 1.5% for the repeated events and 3% for the occasional. This is what we have seen like sometime back. When you start a motor once in a day or maybe once in few days, probably you can go up to 3%. But when it comes to fluctuation every I mean repeated events with a short interval, then probably you need to limit to 1.5% at point of interconnection, not at the location of the motor connected. There you cannot maintain 1.5%, but we are talking about the point of interconnection so that other consumers will not be affected because of motor starting in one of the industry. Okay, so that is what the importance of it. Harmonic distortion limit, you can see here when it comes to the grid 765 kV and I mean 765 kV, 1.5 times the total THD. The individual harmonic distortion is 1%. It should be limited to 1%. And 400 kV slightly more, 2% and 1.5%. And 220 kV 2.5 and 2%, and 33 kV to 132 kV 5%, and 3% for the individual harmonics. Fault clearing time, we talked about it. I mean, when it comes to 765 kV and 400 kV, it should have a proper protection system so that it can, I mean, clear the fault within 100 millisecond. When it comes to 20 kV and 132 kV, it can clear the fault up to, I mean, within 160 millisecond. When a breaker fails to trip, it is allowing up to another 200 millisecond, because when one of the breaker trips, even after the protective relay gives the trip command, then I mean some other breaker need to protect that fault, right? So it takes another 200 millisecond for that, and the grid code is allowing up to additional 200 millisecond when breaker fails to trip. And -1 reliability, the other grid code requirement, stability after a single disturbance even. These are the criteria of grid. And -1 reliability, that if in the grid, I mean up to 132 kV, at least when any part of the grid, I mean any single part of the grid fails, it should not create any interruption to any consumers. Okay, so like how we can achieve that? If you have two feeders, which can take each one take 100% of loading, even if one of the feeder trips because of some differential protection, other feeder is capable of feeding the entire load. So that is a -1 reliability requirement. So harmonic distortion. Okay, so this is the harmonic distortion in general, like deviation in wave shape from the fundamental frequency waveform. This is the I mean, in general about the harmonic distortion. The causes is like the classical sources were like magnetic saturation. If the transformer is saturated, or any magnetic equipment saturated, then it cannot have sinusoidal waveform, so it will have a harmonics in that. Arc furnaces can create harmonics. Welding machines, like arc welding machines, basically it's kind of short circuit, so short circuit also can create harmonics. But I mean, why we are not putting the short circuit, that is expected. But when it comes to the load, as welding machines, that frequently there will be I mean, switching on switching off will be there, so I mean it can cause a harmonic issue. Rectifiers, yes. Yeah, and the modern sources are like on non-linear loads, like wherever the power electronics are there, such as SMPS, inverters, high efficiency lighting, etc. It can create harmonic. These are the source of harmonic. What are the consequences of harmonics? Like increased probability of resonance. I mean, when you have harmonics injected into the system, and I mean the characteristics impedance of the system at that particular harmonic frequencies, either higher or lower, it can create a resonance condition, which means that uh, the distortion becomes much higher when it comes to the resonance frequency stage, and your resonance frequency of the system matches with what is harmonic injection into the system from power electronics devices. So need to have proper study to ensure that resonance harmonics, resonance is not is not happening in the system. So that is one important study for the harmonic harmonic study. It's one of the important factors that we need to look into. Overload and overheating, we talked about it. I mean, when rotating machines runs with harmonics, it can cause an overload. I mean, maybe even the uh, a system like this additional harmonics is additional loading. I mean, you have already fundamental loading, fundamental component loading. In addition to that, harmonic loading also will be there. It can cause overloading, and because of that, overheating also can happen. Loss of efficiency, if there is more overheating, the losses is more, then efficiency is becoming lower. Electromagnetic interference can happen if there is a higher order harmonics. It can cause interference with communication networks. Nuisance tripping can happen in the protection device because of maybe when it comes to triplet order harmonics, like third order, sixth, third, ninth, 11th, etc. the current goes to the neutral of the equipment. I mean, harmonic current goes to the neutral of the equipment, which is generally, in general, there is no current expected in the neutral. So maybe some protection device can maloperate, because it will consider that as a earth fault current if the current is flowing to the neutral of the transformer or the generator. The protection system may get confused, and it may issue a trip command. Errors in measurement also can cause because of harmonics. So impact of harmonics, we talked about it, in general. So, that in detail it is given here, like at different location, like how it can cause an issue. Um, yeah. So this is one of the harmonic spectrum. This is one of the PV inverters of rated output 3125 kilowatt. A power factor range, it can supply reactive power also, from -8 to +8. It can give MVAR into the system also, like within this power factor range. And then for this grid connector inverters, how much harmonic content can be injected into the system. You can see here, this is the harmonic content and tabulated also. So maybe if you see here, THD is only 1.008. Okay, we can say that, when we saw that harmonic THD, that to be limited to the system, it's like a few slides back we have seen that. Yeah, it is here. 1.5, 765 kV, 1.5, 1% is here. But maybe when it comes to 33 kV and down, probably is 5% THD. But when it comes to here, it is giving only 1% THD, right? But what happens? What is the issue here? What is the issue of like when it comes to 1%? Because when you go for a PV plant, we are showing only just one inverter here of 3125 kilowatt. But in a solar plant, you can have n number of such UPSs. Okay, in one of the project which this particular project itself, it has I think around 25 such inverters. 25 such inverters. So what amount of harmonic injection into the system, you can assume, like how much harmonic injection is can be injected into the system. I will show you some SLD which shows that maybe towards the end. But the point is, like at the point of interconnection, not at the point of interconnection, but at the solar plant end, it has a THD of almost like 13% THD, 13% for that plant. But the EHV connection to the grid at a location around 75 kilometers away from the solar plant, and because of that transmission line, it gets reduced. Harmonic injection gets reduced, because maybe the transmission line capacity itself will act as a sink for the harmonic content. And at the level, maybe it is at the grid connection level, it is close to 5% or slightly more than 5% is there. So you need to understand what are the concerns the smart grid integration, because one of the major component of smart grid is this renewable integration, right? So when the renewables are integrating more and more, if you don't take proper steps to limit the harmonic at the source level itself, like maybe you need to limit the harmonics at the inverter level itself, or probably at the max, maybe some harmonic filters at the plant itself. If you don't do that, probably it can cause a big issue at the grid. Okay, that's the concern. So some of the solutions of power quality issues, not just the harmonic issue what we are talking about. For the harmonic issue, definitely the power quality monitoring is important thing. Right now, we do not have enough monitoring system. When it comes to the distribution level, probably we do not know like at what quality of power we are supplying. Utility supplying the power to the consumer. So need to have a proper monitoring system, power quality meters, or maybe now we are doing some smart meters as a part of the, as a part of a smart grid integration, smart meters are being installed. So probably the smart meters will have features, may not be like 100% features what a power quality meter can give you, but at least the voltage can be monitored, and maybe dips in voltage, those things can be monitored at the AMI, the advanced metering infrastructure also. Then, like to control the voltage, you can put some shunt reactors and shunt capacitors, which can control the voltage. Shunt reactors can, like wherever you expect higher voltage because of during low load or something like that, then you can go for shunt reactor there. And a shunt capacitor wherever you expect lesser voltage and power factor is higher. So to reduce the overall loading, to reduce the overall loading and to improve the power, improve the voltage, improve the power factor, shunt capacitors are used at the distribution system. Even in transmission system also, shunt capacitors are used to control the voltage, not to control the power factor. Though when you increase, I mean, when you put the capacitors, power factor also will be modified, but the main intention of putting shunt capacitors at the transmission system is to control the voltage, or to control the reactive power flow. Isolation transformer, as a part of the inverters or maybe power electronic system, we generally go for an isolation transformer in order to isolate. There will be some, there will be delta winding there in the isolation transformers. Definitely, that can isolate all the triplen harmonics. So most of the triplen harmonic and all the triplen harmonics will be isolated because of the delta winding on the transformer itself. So that is another point. And drives, whatever power electronics drives, wherever it's used 6 pulse, it will have more harmonics into the system, injection into the system, that can be changed to higher pulse, 12 pulse or 18 pulse system with maybe 3 winding transformer, 4 winding transformer, etc. You can go for higher pulse drives, and that can reduce the overall injection of harmonics into the system. And filter design, based on the harmonic studies, need to be done whenever it is whenever one of the power plant or maybe industry is unable to control the harmonics at the point of interconnection. It's a regulation also that need to be control the harmonic content within the limits. Fax device like SVC, STATCOM, TCSC, that is also, this is basically to improve the voltage. These devices are there. We can argue that these devices also brings power. A lot of power electronics components, so it can bring the power quality issues also. Yes, that is right. But if you see the SVCs, it will have power. Filters as a part of the SVC itself. So it controls the power quality also at the SVC level, and at the same time, it gives the required amount of reactive power into the system, and also draws reactive power from the system. So let's see some case study. I hope we can discuss this within another 5-10 minutes. So I've taken some typical distribution system. You can see here, generally the distribution substation will be there where the voltage will be, voltage will be stepping down from higher voltage to lower voltage. In this case, it's a 33 bar 11 kV distribution substation with 5 MVA transformer stepping down to 11 kV. And there are many feeders. I've shown only one feeder. The remaining feeders, I'm putting it as a lumped load. So this is one of the feeder wherein you can see like distribution transformers are connected. Maybe it's going to a domestic distribution where it's stepping down to for 15 volt in this case. And there is a load of maybe if you see the transformer rating, 0.25 MVA transformer is the rating for the distribution transformers. And load connect is almost like 80% of it, which is 0.2 MVA. You can see here all the transformers are identical. Load connector is also identical. And but this is located at different places. Maybe I think I've taken 500-meter apart. Like the first transformer comes at 500-meter from the substation, next one from there to 500-meter. It goes like that. Okay, so let us see like what is the voltage profile of this system by doing the studies. This I have modeled in ETAP software. So let's see what is the scenario here. So this is the existing scenario with loading something like this. So you can see here uh, the voltage profile is happening like this. So probably like this transformer is kept at a nominal tap. So the voltage, because of the loading, some voltage drop will be there, even though the 100% voltage is here. There's a voltage drop in the transformer because of that the voltage is reducing to 96.71 percentage because of the drop due to the load current here. And when it comes to here, another voltage drop on the cable, it is further further reduces to 95.73. And on the last leg of, last transformer, it goes to 95.24. But on the secondary side, you are getting 96.42. So you can see like just before it, total load at the substation is 4.08 MVA, and 75 percentage of 80%, 75 to 80% transformer loading. Most of the transformer loading is in that range, and the minimum voltage is 95.24, which is also okay because we are trying to maintain the voltage within plus or minus 90, plus or minus 5% deviation from the nominal voltage. So 95.24 voltage is also acceptable, and 96.42 percentage voltage at 415 volt also acceptable. Let's see like this is the results. Okay, let's see like if you add 20 percentage electric vehicle. You can see here earlier, yeah, earlier this load was taking around 0.19, okay, because of 2.2 MVA loading was there. Okay, now I'm just increasing that loading by adjusting the load parameters. It is increased to uh, I mean 223 kilowatt, or maybe 0.223 kilowatt, or kVA, 223 kVA, by adding 20 percentage electric vehicles. Okay, just simulate a case that 20 percentage EVs added, because of that overall loading has increased. What happens now? You can see the voltage profile is changed now, right? So this is what is going to happen when many households are having electric cars. This is going to happen. So you can see the first part itself, the voltage is reduced below 95 percentage, and when it comes to the last one, it goes 94.27. Even at the LV level, it is 94.84%. This is just as 20% addition of electric vehicles. If we go for higher addition, the situation will be changing drastically. You can see that part also here. 50 percentage addition. You can see the voltage reduced to 92.79 percentage here, and all the places reduced. So, in the LV system, you're having 92.47 percentage. Okay, so you can see that there is a reduction in voltage because of like if some electric vehicles are added up without actually changing the transformer. You can see the transformer is also overloaded, right? Its rating is 0.28 MVA. Right now, the power is flowing 0.281. So, which means that the transformer loading has come to 100 up to 160%. So, what will happen to the system if you don't take any? If the utility doesn't take any action, either to reduce the loading or to increase the transformer size, what is going to happen? Transformer is going to burn, right? It cannot continue to load 116 percentage. Overheating will happen, and one fine date is going to burn. Either the transformer will be burned, or if they have a proper overload protection available for the transformer, maybe either the fuse or probably the breaker. If there's a breaker on the primary, that breaker will be tripping. So that is also going to cause an interruption, right? So this is the concern when, as a part of the smart grid, when more and more EV addition is going to come, because all the governments, throughout the world, is promoting this EV addition because of many reasons, like fossil fuel is getting reduced day by day. So, I mean, and the prices are increasing. So probably, and another part is that carbon emission is another reason. So government has come up with a policy to increase this renewable generation, also the CV addition. They're promoting. I mean, most of the governments are promoting this. So if the utilities doesn't take an action, I mean, it's the local level. We are discussing about the local level, not the overall grid level. We are talking about it. So I mean, all the I mean, utilities has to assess their system available in order to take care of this heavy demand from the EV addition, which can happen within few years down the line. And I don't think that all the transformers, all the distribution transformer can be changed within a few years down the line. So that is almost like impossible. So what is the option now? Let's discuss about the option also. Let's try to compare it like we have already seen it. When existing scenario everything is perfect, future scenario also okay. I mean, future scenario one is when only 20% of VV addition is there. For the particular case what we have studied, it's okay, but in some cases when one of the feeder is already overloaded and if you add 20% in addition to that, it's going to create a problem. But the system what we studied is okay. And future scenario 2 is with 50% EV addition. There the transformers are overloaded. Okay, even the substation transformer is also overloaded. You can see that 5 MV transformer is loaded to 6.14 MV. So substation transformer is also overloaded here. So this condition cannot be possible, right? I mean, so some precaution or some well thought solution should have been there. Otherwise, it's going to cause a problem maybe a few years down the line. Okay, so let's see like what renewable generation can do in this. Okay, you can see here. So the loading we maintain the same 50%, maybe I think in this case 30%. The loading is more when you talk about only this, but here some generators are there. Okay, PV generation is added up here, which gives almost like 180 kilowatt. Okay, so what the power is required from the transformer or the grid is only 181, though the overall power requirement has increased to 279, more than this 250 kVA. It is the transformer is not getting overloaded, right? It is still taking only 187 because you have a solar generation on the local bus itself, so it is reduced. So now you can see here when the solar is added, I mean, it's very close to 95 percentage. Probably if you add some capacitor banks or something at the load centers, you can maintain the voltage well within this 95%. So the solution is simpler there. I mean, if you have a solar, but just because of solar, is it going to solve this problem? Definitely not, right? I mean, it's going to solve the problem only during daytime. But what happens nighttime? For that, you need to have a I mean, you need to have a battery storage system. So that has to come. I mean, we do not have a much options left other than that. Maybe some other storage, maybe not just battery storage. If any other storage is also there, it's fine. But locally, I think that is one of the feasible solution. Like, I mean, maybe some kind of battery storage, and maybe even the electric vehicles can act as a battery storage. That we'll talk about it. Yeah, this we'll talk about little bit about like how the grid should control this overloading issue, and also the voltage collapse that can happen because of overloading. So this is one of I mean, this is actually a typical load curve in Kerala state. And I have actually extrapolated it into, I mean, I got some sample load profile, but I have extrapolated it into match with 4316 megawatt peak requirement, which is recorded on, I mean, this, I mean, 2019. I think now I'm not sure whether it's increased beyond that, but this was the data before that COVID pandemic scenario. In Kerala, this was the value, maximum peak occurred, but because of the COVID next year, not much requirement was there. It was lesser than that peak requirement. This year it might have crossed. I'm not sure about it. So you can see here, this is the profile. So what is the, I mean, generation requirement with the spare capacity? You need to have, I mean, more than 5,000 megawatt generation capability should be there to meet this load at least. Yeah. But if you take a scenario for, I mean, electric vehicle charging without any control mechanism. Like, let's assume that all are going for work, and when they come back after the work, all the battery, I mean, all the vehicles are charging at the same time around 18 hours, which is 6 o'clock in the afternoon, I mean, in the evening. So what is going to happen? We assume that 30% EV load is added to it. So you can see that this curve, this was the original curve, which for 316 megawatt or something, the peak requirement. Now the peak requirement is increased to 5611 megawatt. Okay, though it is not a ideal scenario. I mean, sorry, a practical scenario that all the cars are charging at the same time, but this is one of extreme. Okay, so the extreme is, it says that the power requirement will be increased to 5611 megawatt when 30% addition of EV demand is there. Okay, but if you go for some kind of system where, I mean, utility gives some incentive, or maybe probably they put some penalty to charge a car at this time, and they give some incentive to charge a car during early hours, maybe in the morning time after 12 o'clock or something. If they start charging the car, probably the 6 hours is required to charge the car. You can see here, this is the peak now. This just increased from 4316 to 4815 megawatt, only 12% increase. Whereas in the earlier case, it was 30% increase. Okay. Now, the scenario 3 is like, this is also ideal scenario, which cannot happen. Like if the charging is uniformly scheduled, some scheduling system is there, it is uniformly scheduled, then what is going to happen? The peak demand has reduced to 6, I mean, not reduced, at least slightly increased only. It was only 8% increase from the original. So that is how it is. All these three scenarios can be considered as an extreme scenario, but utilities has to come up with some policies, like to give some incentives to those who charge during morning time, or maybe some kind of scheduling need to be done. Then probably overall power requirement will be much uh, lesser. So the, I mean, utility doesn't need to install more and more generation, doesn't need to have more transmission network, distribution network, and it improves the voltage profile of the system, which is nothing but the power quality will be improved, the voltage will be maintained. But in this scenario, definitely we can assume that the voltage will drastically come down. I mean, if such a scenario happens. And another point is that, which the V2G technology, which you might have heard of it. I mean, electric vehicles can also act as a battery storage system. Uh, it can it can give power to the system. Probably the batteries inside the electric vehicle can be used during peak hours to give power back to the system. That's the another technology is available to also improve the power quality during peak time as a support. And some battery storage also, not electric vehicle. Some standalone battery storage also can help during peak time to give some power requirement. Or maybe some of the battery storage system is used for the transient fault to support the grid, and maybe some sudden tripping of largest generators, then maybe the frequency can go down. Maybe if there are some battery storage system to act during such transient period, it can definitely help the grid, and it can improve the quality of the power. Uh, so yeah, so uh, that was it. Basically, I was trying to give an overview of power quality issues in smart grid integration, and the power quality monitoring. Definitely in terms of harmonics, when we talk about the power quality, the monitoring plays an important role. We do not know, just by seeing the intensity of light or something, we do not know what quality of power we are getting it. So there should be a proper power quality monitoring system, even though it is recommended in India, but I mean, it is not effectively enforcing this requirement. So this is a very important requirement to make the power system more power system with more quality. To know like where and all power quality is lesser, and to go with some mitigating solutions. So definitely the implementation of smart meters or PQ meters can gather power quality data. Analysis of power quality data and installing mitigating solutions will improve the reliability of the power quality of the grid. And I already told that where we stand. There's a huge scope for, or big scope for improvement of power quality in Indian grids when we want to compete with international grids. So there's a huge scope for research into this field. So that's it. Thank you very much for the patient hearing. If you have any doubt, probably we can discuss now if time permits.
Hello.
Sir, very good morning, sir.
Yeah, good
You
morning.
can hear me?
Yes, yes, I can hear you. Please go ahead.
Because, as you said, maybe the 10 years down the line, we have to double the power generation, okay, for the
Yeah,
electronic vehicles charging if it is goes to 100%.
right,
Yeah, but why?
right,
The power generation doesn't have this carbon emission. It does have carbon emission, correct?
right, right. Yeah, you're right. Yeah.
All the big
So,
shots of the world, they are saying there is too much carbon emission due to the petrol, okay, fossil fuels, okay, and they are pushing the world
right.
towards the EV, electronic vehicles. But in at the end,
Yeah,
even for the electrical production also, that too have carbon emission. Does any
right, right.
studies
You
have
are
this
absolutely right.
comparative study that which means mode of operation will be feasible for the whole population?
Yeah, yeah, yeah.
Means the electrical generation at a bigger, means if you are saying that we need to double the power requirement, then it is a huge cost. Okay,
Right, right, right. Yeah,
and
yeah. I got your question. It's a
see,
very, yeah, yeah. Please go ahead. Yeah.
no, but the fossil fuels which we are utilizing now for the last 15 years, I am in
Right.
the Middle East. Okay, I am calling you from Middle East.
Okay.
I am here in last
Right.
22 years. So
Right.
this is they will finish. It will finish. Okay,
Right.
and nobody
Right.
knows exactly the quantum of the quantity they have balance.
Right.
Okay, and
Right. Right.
the
Yeah.
whole the big shots, and I'm working in an MSc. Okay, so the whole big
Right.
shots are
Okay.
pushing the whole world towards the EVM. Okay, go for the EVM, go for the EVM. It is not means like a country like India. It is, if you want to make the power generation double, just imagine the means cost incur for the means, infrastructure.
Right.
So
Right. Yeah.
instead of that, can we not have any other ideas that to have this? And, it is not necessary to increase the utilization of the vehicles. There are some other
Right.
ways also by which government can facilitate the people from
Right.
moving from one place to another place.
Right. 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 Yeah. 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 It's a very important question, and even I had this doubt some time back. But the point is that okay, like all the big players are saying that we need to come up with a lot of electric vehicles. The entire industry has to be changed to the electric vehicles. And nowadays, the governments are giving incentives or maybe some reduction in tax, etc., to bring this electric vehicle industry on a much faster level. Though I would say that it did not come the way it was expected. But nowadays, you can say that it is increasing. But the point is that when we say that electric vehicles, we should not. We have to see that two things. Goes hand in hand. Okay. One is electric vehicles. I'm getting some disturbance. Am I audible?
Yeah, you are audible, but somebody else is having
Yes.
the mic on.
Right. Right. Yeah. Yeah. So there are two technologies should go hand in hand, or maybe both the technologies should be promoted at the same time. Okay, that is what we are discussing also. One is electric vehicle industry, but just with the electric vehicle industry, the carbon emission cannot be reduced, because carbon emission may
Yes,
be
yes.
reduced from one side to another side. Maybe at the power plant
Another
end,
side,
it's
it will
going
be
to have
shifted. It will be shifted from fossil fuel to the generation side
Exactly,
of the
exactly.
electricity.
Exactly. So, but how to control that is only the solution is the renewable energy generation from the solar and wind. And since you said that you are from Middle East, the way the Middle East, especially this UAE or the Dubai, is moving towards the renewable generation, their total power requirement is almost like 10,000 megawatt. I mean, it's less than. I mean, the peak may be lesser than that. Maybe your installed capacity is around 10,000 megawatt. Maybe the peak requirement may be 6 to 7 thousand megawatt. Right now, they have already came up with almost like 20%. I mean, 2,000 megawatt approximately the power generation. Their plan for 2030 is to go for 5,000 megawatt renewable generation. So what you are expecting, and they are going with a lot of power, I mean, storage schemes also. One is battery storage itself. Second one is this pumped storage. I mean, they have a dam in one of their area, wherein they have a pumped storage system. I mean, power will be generated during the peak time, or maybe when solar is not available. And then the water will be pumped back to the dam during the I mean morning time, where they have the solar power available. Okay, so these are the technologies which need to be promoted. I mean, nowadays, I mean, Indian government and almost all the governments are promoting both together. One is the electric vehicle industry and also the renewable generation. Without this, one thing is that carbon emission part. The second part is that the infrastructure itself is not adequate to connect all the vehicles to the grid. I mean, to go for all the electric vehicles. I mean, even though there is money, I mean, there are issues with the, I mean, right of way, etc. And there are issues for putting this substations also. So you need to, I mean, you need to generate the power locally through this conventional, I mean, non-conventional methods, solar or wind. And solar is, I mean, becoming more and more economical nowadays because of reduction in the panel cost. I mean, inverters, etc. So, I mean, that is going to be the future of power system, like more a lot of solar or maybe the wind generation locally available, and so that the fossil fuel requirement can be reduced. And many countries have already achieved. I mean, at least during daytime, they can just supply the loads from the solar sources or renewable sources, but it is not possible to disconnect the fossil generators because of stability issues. But still, on a net energy part, probably they can achieve this during morning time. So these two policies, I mean, these two technologies, one is electric vehicle technology and the renewable integration part should go hand in hand. Then only you can say that, I mean, we can go for a better, greener world. I hope that clears the query.
No, my request is, why don't we go for some new innovations? Means it is not electrical vehicle or generation. See, electrical
Right.
vehicle
I
you are
mean,
promoting means you want to have a one vehicle per one person. Means like we have in the Middle East. It is not at all possible in India. So in
yeah, definitely.
the big country like India, we have to go for some other ideas. And I think this webinar or this session is in a college, correct?
Yeah,
It's
that's
for a
right.
college, correct? So let our students means go for some new ideas. Not to the world. The world is means pushing whatever ideas they like. My
Yeah,
request
it
is
is.
that we should have some new innovations. That's it. And nobody talks about the solar maintenance. Solar power is okay, easily generated in the this deserts of Middle East countries. But like country in India, it is not that much feasible. If you see, we don't have means if the weather
Land.
conditions are not like the Middle East, like the African continent. The weather conditions in India is bit different. Only during the summer times, maybe you have the maximum load generation from solar, but during the other seasons, it is compared to the capacity and compared to the requirements, it's negligible.
Yeah,
So
you're
we should
absolutely
have
right. I mean, some mass transporting system, or maybe reduce the transportation requirement.
yes.
Probably,
This is
yeah,
what I
that
want to
is
say, that the transport system and
right.
the thinking of the people should be changed. See, we are using here in Middle East,
Right.
person have four vehicles, five vehicles, because the petrol was cheap before. Now they are also making it costlier, so that the people tend to move to the common transport system or the public transport system. Which in that way we have to take
Yes.
our populations. So that will ease a burden on them, burden on the community, burden on the governments. It is not as we say that down the line 10 years we have to double the capacity of the power capacity what we have achieved at this moment we have to go back to 20-30 years back. From there it started. Now we reach this point, and if we need 10 years double the capacity, it's not as easy as we think.
Right. Right. It's a very valid point. Thank you. Thank you very much. Any other queries?
Thank you, sir. Yeah, I'm from Middle East. I'm in Riyadh.
Thank you.
I've done my studies from Bangalore.
Okay. Good.
Thank you. Was any other questions you can take up?
Yeah. If there is no other queries, let me conclude. Thank you. Thank you very much
Thank you.
for
Thank you,
giving
sir.
me this opportunity to present. Yeah. Thank you very much.
Thank you, sir. Session is very nice. Thank you for your valuable presence. Thank you, Dijo, sir.
Yeah, thank you. Thank you very much. Thank you very much, the management,
Sir, one
for
more
being
request.
accommodating.
Can you extend this kind of sessions to
Yeah,
other
please.
parts of India also, like other cities,
Sir,
major cities where we have?
this is meant for all over India. The participants from various parts of India join using Atal FTP login.
Okay. Thank you.
This is
Thank you.
meant for whole
It's a
India.
very good, very good session, and uh, for the students of the college it is very informative, and too much of learning is there in this kind of session. We missed this when we were studying. Thanks,
Yes, sir.
sir.
Yes, sir.
The
Thank you
guys
so
who
Thank
much,
have
you.
sir.
arranged this. Thank you.
Thank you.
Participants,
Thank you.
again.
Thank you.
Okay, sir. Okay, sir. Participants, thank you. Again, next session will be start exactly by 11:30, handled by Dr. V. Karthikeyan, professor from NIT Calicut. So all are requested join sharp by 11:30 a.m. Thank you for patient listening. Again, we will meet by 11:30. Thank you all. If there is any problem with feedback link, please inform me. So I already shared feedback link in in-call message. If there is any problem with feedback link, please inform me. So I will check it whether it's working or not. Thank you all.